Okay, so we are going to do the next set, which is going to essentially be 41 all the way to 60. I just want to mention really quickly, work is equal to pressure times delta V, or change in volume. Essentially force, pressure is a force over the displacement of something. So that's the delta V. Kilopascals, there's a number of ways that you can look at this. The units need to be pascals and meters cubed. That was correct in order to make this happen. The other, I don't know what conversions you all will have for the exam. So 101.3 joules is equal to 1 liter atmosphere. So that's also a conversion that you can do. So if you're given this in atmospheres times liters, you can essentially just use this as a conversion factor. So that's going to be an important one. You should have this, but I'm not sure that everyone does. So that is how you solve that one. All right, moving on. So a 4.25 gram sample of cyclohexane is combusted in a bomb calorimeter. Okay, the bomb calorimeter essentially just measures, it absorbs all of the energy in the form of heat. So here's my little container. I put my little sample in here. I hit it with a charge, right? Positive, negative. I send a little electricity through, and this whole thing is filled up with water. And so your sample will essentially send heat into the water will heat up. So we are measuring the temperature change, or we're measuring the heat gained by the water, and that came from the sample. That's the idea. So combustion is involved. So a 4.25 gram sample of cyclohexane is combusted in a bomb calorimeter. So there's your sample with a total heat capacity of 5.86 kilojoules per degree C. The temperature of the calorimeter increases from 23.5 to 39.8. What is the heat of combustion of cyclohexane? So again, the idea being that you are releasing energy into the environment by burning it. And so here we go. And again, we really do look at the unit here, kilojoules per mole. We have a gram sample, so we are going to convert this into moles. And by converting this value into moles, that's going to be the bottom portion of our math here, ultimately. So we are looking for what is the heat of combustion, or the delta H of combustion, or the heat Q of combustion is another way of putting it. Ultimately, it's just the energy involved. So the units that we're going to need are kilojoules on the top, and so we're going to have to plug that number in, and moles on the bottom. So let's start with the moles. So as long as you have the units, and essentially we're going to be in pretty good shape. I don't know why that's underlined, but because I was highlighting. Anyway, so moles. So if I have a 4.25 gram sample of cyclohexane, I know carbon, we can just essentially do the math. Carbon 6 times 12 plus that 12. So it's going to be ballpark again. 6 times 12 plus 12 gives us, oh, that's not right. One more time. 6 times 12 for the carbon, so 12.01, right? Plus the 12 for the individual hydrogens, so 84 grams per mole. So 4.25 grams times fraction, grams in the bottom, which was 84, moles in the top, 1 mole on the top. So 4.25 divided by 84 gives me 0.051. 0.051 moles. So that's how much cyclohexane we have. So that goes on the bottom, 0.051 moles of cyclohexane. Now we need to determine the energy. And if we look at the unit, we're going to see that this bomb calorimeter, for every degree C, we're going to see a 5.86 kilojoules of energy put into the environment. So we need a delta here. What is the delta T? Final minus initial, 39.8 degrees C minus the 23.5 degrees C. So 39.8 minus my 23.5 gives me 16.3 degrees C you go 0.3, point, zoom in, 0.3 degrees C. So 16.3 degrees C, that's the total temperature change times the, I'm sorry, I've got so little space here, 5.86 kilojoules per degree C times degree C, which is 16.3 degrees C. And that's going to, degree C cancels, and we're going to get our total energy change. So multiply 16.3 times 5.86 or vice versa. Here we go, 95.52 or 95.5 kilojoules of energy is released by just this sample. But we're going to normalize it to a mole. So I'm going to plug that in here, 95.5 kilojoules. So divide that, 95.5 kilojoules divided by the 0.0501 gives me 1,906 kilojoules of energy. So we can eliminate those two right off the bat. So now the question ultimately is this a positive or a negative? And because the water heated up, the energy is going from the system, being the cyclohexane, to the surroundings. So we are going to call that one C. So we've got C for the answer here. All right, moving on. In a coffee cup calorimeter, and so this is another calorimeter one, same idea, 50 mils of 0.1, you usually do a lab on this. So I have some amount of sodium hydroxide, and it looks like the same exact amount of HCl. There's a temperature increase by 14.9 degrees C. What is the enthalpy of reaction? So for this reaction, we're going to use a density of 1 for the water, and we're going to assume also the specific heat capacity of this thing. And again, we're going to focus on units usually for this. And so off we go. Again, we're going to look at our unit, and the units that we're looking for, kilojoules per mole. So we need energy released as a function of the number of moles that have reacted. So we can get moles from either one of these because they're both limiting, or they're both going to run out. So volume in liters times concentration, because it's 0.100 moles per liter, 1 liter. Liters cancel, and I am left with 0.5, right? Or 0.05 rather, 0.005. So 0.05 times the 0.1 gives me 0.005 moles of energy. That's going to be on the bottom. So my 0.005 moles, that's the total reaction consisted of only 0.005 moles from the NaOH or the HCl, that's fine. So we just need to substitute kilojoules into the top of this. And so if we look at heat capacity, the joules of energy released, right? So we'll start with that. We don't need to know any equations, it certainly helps, but 4.18 joules per gram times degree C. So what I need to know is I want grams and degree C to go away. So let's get rid of the degree C first. I know it was 14.9 degrees C. Degree C cancels. Next up, I need grams to go away. Well, this little section where it says density, we have 100 mils of water, which is equal to, in this case, because it's 1-to-1, 100 grams of water, because the water is what we're seeing the temperature increase in. So 100 grams of water, grams cancels, and we're left with joules of energy. Look out for this in the end. So 4.18, right, that was 4.18 times 14.9, enter, times 100, enter, gives me 6,228, so 230 joules of energy. But we need this in kilojoules. So let's convert this to kilojoules, which is just move the decimal 3 times, 6.230 kilojoules. So 6.230 divided by 0.005 gives me 1,200, 6.23 divided by, 1,246. And again, the energy is released. So we should have pretty much the only answer here. And So D for this one. Released energy released into the solution because it's heating up, right? It's an exothermic reaction. All right, next one. The enthalpy of reaction, so we have a reaction here, is, okay, so that's how much energy for every single one of these. What the enthalpy of the reaction below? Okay, so, all right. This reaction, as written, produces that much energy, that many kilojoules of energy. So what we're interested in is how does this reaction, reaction 1 versus reaction 2, differ? How are these two different? So how do I go from reaction 1 to reaction 2? So let's focus on that idea, and then we're going to talk about the actual answer here, because they have to be slightly different. So here we go. So let's just look at what we have in terms of, let's focus on this, C2H5OH. We're going to notice that this is a product. So in order to switch these two reactions, we have reversed them, right? Because C2H5OH, the ethanol, was a reactant. Now it's a product. Okay. So focusing on that, keep in mind we're going to change it a little bit more. But if the original reaction is negative 1418 kilojoules, what do you think the energy change is going to be if I reverse the reaction? So if I switch it, well, the reverse reaction is just going to be a positive 1418 kilojoules. So whenever you reverse the direction of the reaction, the energy is going to switch signs. All right. So now the other thing is this has a 1 in front of it, and this has a 1/2. Okay, so that means ultimately that we have essentially multiplied this reaction by a half. So we've only looked at a half of the reaction. And so the other thing to think about is if this reaction releases this much energy, if 1 mole of ethanol releases this much energy, well, that means that half the reaction is going to release half of that energy, right? So what's that? 709 kilojoules of energy. So we have these two things happening. By reversing the reaction, we are flipping the sign. But then if we take that reverse reaction, which we had, and we also have it, we're going to end up with a positive 709 kilojoules. This number here was from, well, this negative number here was from the original reaction. So that's what you end up with. We should have a positive 709 kilojoules for 43, D. All right, moving on. The main engines in a space shuttle burn hydrogen to produce water. Okay, great. How much heat is associated with this process if 1.32 kilograms of liquid hydrogen is burned? Okay, so liquid hydrogen is burned. And the way that we want to look at this is there's a couple, this is a stoichiometry problem, only we're going to include energy in it. The way that we can look at this amount of energy is based on the coefficient out front. So essentially, 2 moles of H2 is equivalent to producing negative 571.6 kilojoules of energy, releases that much energy. And so then this just becomes a stoichiometry problem. I'm going to take my 1.32 times 10 to the 5 kilograms. I'm going to convert that to grams. I'm going to convert that to moles with its molar mass. And then I'm going to convert it to kilojoules using this conversion. So this is just a multi-step conversion, converting from one to the next. And I guess I can write it out, won't harm me. So 1.32 times 10 to the 5th kilograms times fraction. I want kilograms to go away. I want grams to remain. 1,000 grams is equivalent to 1 kilogram. Kilograms cancels. So we're in grams of hydrogen right now. Next up, I want grams of hydrogen to go away. I want moles of hydrogen to remain. 1 mole of hydrogen is worth about 2 grams, right? Look at your periodic table. Grams go away because it is H2. And then finally, we do have the conversion for every 1 mole, or for every 2 moles of H2 is equivalent to negative 571.6 kilojoules. Okay, so moles cancels, we're left with energy. Okay, so it's a ton of energy, should be a ton of energy. It's a rocket ship for that matter. So the answer you should get is C. A lot of energy. That's what you get. All right, moving on. Given the following reactions, okay, so we've got a bunch of delta H. What's the delta H for the new reaction? I've got reaction 1, I've got reaction 2, and I have a new reaction 3. What I want to do is I want to essentially combine the reactions 1 and 2 in order to get 3. So the way that we're going to do this is we're going to focus on these things one at a time. We're going to focus on NOCl. Let's find it above. There it is in reaction 2. So does it need to switch sides? Do I need NOCl2 in reaction 3, NOCl is a reactant. So I need to reverse the direction of reaction 2. So we definitely need to reverse the direction of reaction 2. And so if we reverse the direction of reaction 2, that's going to change my delta H to positive 38.6 kilojoules. All right. Next up, I also noticed that I need to have a 2 out front. That means that I need to multiply this reaction by 2. So if I'm doubling the reaction, I'm also doubling delta H. So my new delta H is 38.6 times 2. So we end up with 77.2 kilojoules. Okay, so there we go. That right there, by doing that, that took care of my NOCl. So that puts NOCl in the right position. That is taken care of. Next up, I need N2 as a product. Do I have any N2 already? I do not. So I have N2 as a reactant in this one. So this one also needs to reverse direction because I need to switch it. So that means the sign changes from positive to negative 90.3. I'm sorry, there's not enough room on here to do this. It's just a very tight. And I also need 1 mole of N2. So that means that I'm going to also double this one. So that means I'm going to have negative, so times 2, I'm going to have negative 180.6 kilojoules of energy. So there is my reverse reaction. And generally, when you get the first couple, O2 is here, also the same thing. So that's going to take care of it. And Cl2 is actually here. It's going to take care of it. So now if I combine these two reactions, if I actually write them out, you're going to find out that what's left over is the NO is going to cancel, and you're going to be left with our new reaction 3. Okay, so now what do we do with these two values, the negative 180 and the 77, once we get them? Well, then it's just a matter of adding those two delta H's together. So delta H3 for reaction 3 here, okay, is equal to negative 180.6 minus 77.2. That's positive, right? Or plus, there we go, plus 77.2. So you end up with negative 103.4 kilojoules. The answer for this one is C. Moving on. Ethanol is used as an additive. Okay, we don't care. What is the delta H for the reaction of the combustion, for the combustion of ethanol? So products minus reactants. Okay, so products minus a delta H of formation. The energy involved here is typically going to be a summation. So excuse me for just 1 second. Okay, so the reaction for this, delta H of reaction is going to equal the summation of the moles times the delta H for all of my products minus the summation of moles times delta H of my reactants. So in this case, delta H of reaction is equal to, a summation is just basically doing that math for all of them. So my products, I have 4 moles of CO2. I'm going to use the units for the first one, and then I'm going to ignore them. 4 moles of CO2, and CO2 has a negative 393.5 kilojoules per mole of to form it. plus, so there's the summation part, 6 moles of water times, now this is important, this is liquid water. We want the liquid water one. In fact, I don't think we have any gaseous water, so we can just ignore this one altogether. So liquid water, because phases are important, negative 285.8 kilojoules of energy. And so if we look at, we're just going to look at units. All of the units are going to come out the same. Moles cancels, and we're left with every single one of these moles times delta H's is going to leave behind kilojoules. That's the energy. So this is the total energy of products, okay? 4 moles of CO2 plus 6 moles of water. All right. Delta H, so minus summation of reactants. So this is all going to be reactants. I'm going to try to fit it in here the best I can. So I have 2 moles of ethanol. So 2 times the ethanol, which is negative 277.6 kilojoules of energy, plus, this is the easy one, 6 moles of O2. We don't have any value for it, but it turns out something in its elemental state. So oxygen, O2 gas, hydrogen gas, H2 gas, fluorine gas, all of those, they have a 0 delta H of formation because they're already formed, essentially. And so there we go. There's the answer. So you're just going to sum up these. You'll sum up these, do the math, and you end up with, for 46, you end up with an answer of C. So negative 2,734 kilojoules of energy. All right, next up. What is the wavelength of an X-ray? Okay, so wavelength of an X-ray with the frequency. So we have a frequency, by the way, hertz is per second. That's the unit there. And we want these in nanometers. We often want these in nanometers, okay? So frequency of an X-ray with, so frequency, all right. The speed of light is equal to 3 times 10 to the 8 meters per second, okay? In order to get the speed of light, okay, essentially you need both per second, you need hertz. You can always use constants you know to determine what the equation actually is for this if you're not provided it. Speed of light is meters per second, and we can actually use that to our advantage here. So I need meters on the top, so I essentially am going to take, and then hertz on the bottom. I said that hertz is per second, so C is equal, C is equal to the wavelength, which is, wavelength, which is going to be in a distance, so meters, so wavelength, times frequency. And so the units here, if we focus on the units for just a moment, wavelength is going to be in nanometers. That's what we're going to want, but wavelength in meters, and the unit of frequency is in per second. Together, meters times per second is going to give you meters per second. So we can always use the speed of light to determine what the equation is supposed to be for this. And so what do we know? We know that C is 3 times 10 to the 8 meters per second equals the wavelength, which we're looking for, times frequency, which is 4.2 times 10 to the 18th hertz. And so we're going to rearrange this. I'm going to divide both sides by the frequency. And so your wavelength is equal to, so if I take 3 times 10 to the 8, 3 exp to the 8 divided by 4.2 exp to the 18th. I guess I could have done this math. We're going to get 7.14 times 10 to the negative 11. That number seems correct. Meters. Great, we have our answer. So now what we have to do is we have to determine which one is correct. Because we're looking for nanometers, we can convert this. Okay, 1 meter, which is want to cancel, is 10 to the 9th nanometers. Okay, or we could just simply say those go away. Clearly, it's not in meters. The answer is going to be B. Right? Yeah, good. What is the electron configuration for bromine? Okay, so the electron configuration for bromine, if you look at your periodic table, you're going to have to refresh yourself on this. We're going to go by row. 1s2, 1s2. Oh, let me back up. Let's just find out what's different out of all these. 1s2, they're all 1s2. They all start with 2s2. They all start with 2p6. So nothing has changed at 3s2, 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 3p6, 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 4s2, 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 4s2. Okay, so now we can just ignore the rest of it. We can essentially just go out to 4s2. Let me pull up my periodic table. So 4s2, so that gets us to calcium. Okay, so if you're looking at calcium now, suppose I can share this. If we look at delta H, all right, sorry, if we look at our periodic table, we are at calcium right now. Go share. And we are at calcium right now, and we are trying to get to bromine. We have to go through this first row here. This first row is 3D, right? So if this is the 4s, this becomes the 3D, and then we move back into the 4p. Okay, so we do have this transition to go through, and there we go. So we do go through the 3D before getting back to the 4p. So the next should be the 3D. Let's take a look. And again, I would refresh yourself on all of this. But the 3D, so anything that is not 3D is just going to get clipped. So 4D10, so we can eliminate those two. So 3D10 and then 4p. And we actually don't go to the end of the periodic table. This would be the noble gas at the end. It is not an ion, it's just bromine. So we have C here. What is the ground state configuration for vanadium? Okay, so if you look at find vanadium on your periodic table, we look and see that argon is the thing above it. So that means anything without argon can be eliminated. So we can just get rid of A and B because krypton it's actually beyond vanadium in terms of where it is on the periodic table. And so the question ultimately is, do I have a 4s electrons or don't I? Because they both have 3d3. And you should. Notice that vanadium is 5 elements in from potassium, or total from potassium. So C should be answered there as well. Which element's 4+ ion would have the following electron configuration? Actually, the simple way to do this is 4+ means that it is missing, it has lost 4 electrons. So 4d10 means that if you add those 4 electrons back, you're essentially just going to be 14 elements into the 5th row because the 4d is on the 5th period. Okay, so that would be tin. Done. Tin. You can do this in a number of ways. The 4+ is tin. We love those stable full shells. Nature loves a full shell. Okay. All right. What is the charge and electron configuration of the ion formed for phosphorus? Okay, so phosphorus. Phosphorus is, we're just going to do the noble gas configuration. It's on the row after neon. So we're going to do neon. Nothing, we can't eliminate anything. Then we start to fill up the 3s. So 3s2, 3p3. So this is the neutral phosphorus. Okay, so that's just neutral phosphorus. We see that phosphorus is in group 15. So group 15, that means that really 5 electrons. So you have a choice. Do you want to lose 5 or do you want to gain 3? We're going to gain 3. That means that phosphorus is going to form a 3- charge, right? So it is actually going to gain 3 electrons. So nothing changes, neon's still here, 3s2, 3p. In order to gain electrons, I need 3p6. So we do expect it to be 3-, so we can eliminate C and D. It actually gains electrons, so we're going to call this A, -3 with the configuration 3s2, 3p6. What is the electron configuration for iron 2 plus? Okay, let's do it. So iron is on the row before argon. So anything without argon, nope, they all have argon. Perfect. Next up, 4s2, because that's the next line after argon. 3d, and iron is 1, 2, 3, 4, 5, 6 in. 6 in from in the D block. Because it's forming an Fe2 plus, I'm positive I lost an electron. It lost 2 electrons. So I'm going to eliminate 2 electrons from here, and I'm going to say 4. That should be your configuration. 4s2, 3d4. Okay. 4s2, 3d4. So here's the thing. 4s2, 3d4. So it could be this one, or it could be this one, because they both have 6 electrons in the shell. So here's something to remember. So if this is the shell, if this is the actual configuration, we need to actually, this is not the actual configuration. This is the neutral one, but we actually have to rearrange this. We always should rearrange this. We always rearrange it in order of the lowest one first. So 3D actually would be, sorry, let me back up. Before we, this is the neutral configuration right here. The actual proper neutral configuration is rearranging the shells. So we put 3d6 and then 4s2. We always limit it based on the, we always put it in order of the numbers out front. So 3 comes before 4, so we just flip those around. So this is the proper electron configuration for iron in its neutral state. So if I'm going to eliminate 2 electrons from this, I'm going to eliminate them from the outer shell. So you always rearrange this. You should always rearrange this. Always rearrange this, the lowest number first. So actually this is the proper electron configuration after it's rearranged. So although technically we would probably be okay with it, it's not. C is actually going to be the correct answer for 52. A little bit of a caveat, because you do have 2 positions with 6 electrons. Consider this isoelectronic series. Isoelectronics, just simply the same electron configuration. That's it. That's all it's saying. Which particle is the largest? Okay, so we're talking about ion size. If we think about particle size, I've got a nucleus and I've got electrons that are on the outside. The higher the charge, all of the electrons are the same. So we don't have to worry about the electrons. They all have the same cloud. But the higher the charge in the nucleus, higher positive charge means that this is going to contract more, right? So if I have a 10 charge, the higher the charge, the more it's going to pull it in. And so what that ultimately comes down to, if all of these are isoelectronic, calcium, the one that's the highest positive, is going to do the best job of pulling things in. The higher the positive, the better it's going to do at pulling things in. So 53 should be D. Oh, I'm sorry. Which of the following is the largest particle? I was saying the smallest. That's my fault. I just double checked my answer. So calcium is the largest. Largest. Oh, sorry. Calcium is the smallest, right? Because it's pulling these in. So my explanation was the same, but chlorine is the largest. There we go. Whoa, almost caught off guard there. Chlorine is the largest. All right, moving on. Which of the following is diamagnetic? All right, another word that we need to know, another definition. There are 2 words, paramagnetic and diamagnetic. So if I have a p orbital and everything is paired up, that's diamagnetic. Paramagnetic is if I have any unpaired electrons. So this right here, because those two are unpaired, that is paramagnetic. So we're going to do the electron configurations of these, see which one has unpaired electrons in their orbital diagrams when we draw them. And there we go. That's how we determine this one. So I'm not going to do these because I want to cruise through this. So D, turns out D, both of those are going to be considered paramagnetic. So we'd check both of them and they would both have unpaired electrons. Paramagnetic things will interact with a magnetic field. That's why certain things don't get set off walking through a metal detector, certain metals, because they're just not paramagnetic. All right. Which of the following represent the lattice energy for aluminum chloride? Lattice energy, what does that mean? Well, first of all, lattice energy represents the solid of aluminum chloride. So we can pretty much eliminate B and C right away because we know that we're forming aluminum chloride solid. Okay. So a lattice energy is essentially taking two gases. You actually turn them into ions first because lattice energy is for an ionic substance. So we need to turn them into ions first. We basically make them gaseous, take them, turn them into we ionize them and electron affinity them to turn them into ions, and then we have them. So solid, so it's going to break it down to that, but we also need to bring it together for ions. So 55 is going to be D as well, because we need to turn it into ions because we form ions. This is the starting point right here, but it's actually asking the lattice energy, the last part of the equation. All right. Which of the following will have the highest magnitude lattice energy? Okay, so the lattice energy, and again, I'm not sure if you're given this equation, but make sure I get it right. Lattice energy, the energy of the lattice is equal to a constant times charge Q1, Q2, charge of the positive charge and the negative charge, all over the radius squared. So if we consider this equation, the higher the charge equals a higher the energy. Also, the smaller the radius, right? If the denominator in this is smaller and smaller and smaller, that equals an increase in energy as well. So, and it's usually charge is kind of the biggest determining factor. So charge is not going to be here. +1, -1, +1, -1, +1, -1. All of these are +1, -1. So what it's going to come down to is radius. Which one of these has the smallest radius? So they all have bromine. So actually it's going to come down to, this is going to be C, because bromine is going to be the same for every single one, but lithium is the smallest out of that group. So if lithium is the smallest, it's going to have the smallest R squared, and therefore we expect that to have the highest lattice energy. The closer they are together, the tighter they're held. Okay. Which of the following has the element with the highest electronegativity value listed first? Okay, electronegativity. We know that fluorine in the upper portion of the periodic table has the highest highest electronegativity value. So fluorine. So, and then down to cesium with the lowest. Okay, so we are going to look at our periodic table and essentially determine which of the elements has the one with the highest electronegativity listed first. So if the first one is closer to fluorine, that means that it's going to fit the criteria for this. So 57, so C. Oxygen has a higher electronegativity than, and we could just do that for every single one. Which of these has a higher? Magnesium is closer to fluorine, nitrogen is closer to fluorine, boron is closer to fluorine. C is the one that does not belong. So C has the higher of those. All right. How many valence electrons for the Lewis structure? CO3 2-. Okay, drawing Lewis structures. Okay. We always count. I have 1 carbon, so 4 electrons. I have 3 oxygen, So 3 times, there's my oxygen, 3 times the 6 electrons for oxygen, right? And then I have a charge of plus 2 electrons, because I've got that little charge there of 2 electrons, right? So, so 12, 18, 2 to 24. So 24 electrons for this. Yeah, 28 electrons for this. And that should be trigonal planar too, by the way, if you wanted to make that. Which of the following has the correct Lewis structure? Okay, you got to draw Lewis structures. You got to know how to draw Lewis structures for HCN. So step 1, number of electrons. We're going to count the electrons. Step 2, we're going to central atom. We're going to draw a skeleton. We're going to draw a skeleton of what this looks like, with the most electropositive at the center. Carbon, by the way, always in the center. 3, we're going to take care of the peripheral atoms. 4, remaining electrons to the central, meaning to center. And then 5, multiple bond if needed. Happy to help you go through this if you need to, but let's do it. So HCN. Hydrogen is 1 electron plus the 4 electrons from carbon plus the 5 electrons from nitrogen for a total of 10 electrons. So in my final structure, I'm going to have 10 electrons. Step 2, I'm going to draw the skeleton. Carbon in the center, hydrogen on one side, nitrogen on the other. Done. I have just used, each of these represents 2 electrons. So I just used 4 electrons. I've got 6 electrons left. Next, take care of the periphery. Hydrogen is fine. Hydrogen always needs just 1 bond and that's it. Never add anything else to hydrogen. 1, 2, 3, 4, 5, 6. Nitrogen is happy. It now has 8 electrons. I have no electrons left. So step 4, add remaining to central atom. I don't have any left to add. So my question to you, is carbon happy? Does it have a full octet? It does not. It only has 4 electrons. Each bond holds 2. It's got 4 electrons. So I'm going to share with a neighbor. I'll eliminate that one from nitrogen and put it between them. Nitrogen still has 8 electrons. 2, 4, 6, 8 electrons. Carbon now has 2, 4, 6, 8. Or I'm sorry, 2, 4, 6 electrons. So carbon is still not happy. Let's eliminate another one, create another bond for a triple bond. Let's check. Carbon 2, 4, 6, 8. Nitrogen 2, 4, 6, 8. Nitrogen is happy as well still. There's your Lewis structure. So looks like C for this one, right? That's the correct Lewis structure. Rank the following in order of increasing bond polarity. Okay. Notice that NaCl is last. NaCl is ionic, so it makes sense that it's last. And so we can essentially just ignore this, okay, because it's all the same in that one. Increasing bond polarity. Out of all of these, which one is not polar at all? Well, fluorine and fluorine, they're both an equal sharing of electrons. So it has to be one that contains fluorine first. And so now the question is, what has a greater, well, fluorine or hydrogen is the same on both sides. Fluorine is the most electronegative atom. So we expect to see fluorine in this position. So D for 60. There we go. All right, so that's it. One more video to come, I believe, and that should take care of it. Ah.